Using Digimac technology, the Bloodhound system combines a digital morphologic analyzer, cell counter, and classifier into one instrument that also makes and stains its own slides. This process starts with the printing, where a consistent known quantity of blood is printed onto a custom glass slide. The Bloodhound system is designed to print a uniform monolayer of cells that will dry before further processing. After printing and drying, each slide is stained using a proprietary fixative and Romanowski stains. The sample is then rinsed and dried before imaging. With the slide now ready for digital imaging, each sample is scanned using low-power spectral imaging, where multiple wavelengths of light are used to digitize and count cells from hundreds of images. First, white blood cells and nucleated red blood cells are counted. Because we are using a known quantity of blood, the Bloodhound system is able to count cells within the monolayer to determine the total number of cells expressed in cells per microliter. Next, the red blood cells are counted in the same area of blood to determine the number of red blood cells per microliter. In the last step of low-power imaging, platelets are counted. In addition, this count includes an estimate of platelets within clumps to determine the total platelets per microliter. After low-power imaging, the sample moves on to high-power spectral imaging, where a digital differential is performed on at least 600 white blood cell images, except in the case of extremely low white counts. White blood cells are classified into 5 normal cell groups, while cells that cannot be classified within these 5 groups are flagged as unclassified. The system analyzes each white blood cell in the high-power images by measuring several features of the cells and their nuclei. Using these features, the computer then determines the cell type. The Bloodhound system is trained to recognize the 5 normal types of cells: neutrophils, eosinophils, monocytes, lymphocytes, and basophils. Any cell that falls outside these groups is designated as unclassified, and the technologist can later view the images of these cells to determine their cell type. Hemoglobin is determined by measuring the optical density of each cell. Because we are working with a known quantity of blood, we can determine the total hemoglobin. Next, optical density and size measurements from the multiple wavelengths determine the volume of each red blood cell. The mean of all measured red blood cell volumes is the sample mean corpuscular volume. Similar to the red blood cell measurements, the mean platelet volume is calculated from the mean of the volumes for each platelet identified in the high-power images. Finally, again using multiple illumination wavelengths, reticulocytes are identified and counted based on various features measured on the red blood cells in the high-power images. After red and white blood cells, platelets, and reticulocytes have been identified, counted, and measured, the system can now calculate the entire set of CBC parameters. The red cell distribution width is the standard deviation of all the individual red blood cell volumes divided by the mean corpuscular volume. The red cell distribution width standard deviation is also available. In all, there are 26 different parameters within the Bloodhound system CBC. These results can then be viewed on the viewing station, and results can be shared and stored for later review. Thank you for watching. For further information, please visit our website, bloodhoundcbc.com.